Welcome everyone to another online causal inference seminar. We are very excited today to welcome Jose Zubizarreta from Harvard University. Jose will be talking to us about bridging, matching, regression, and weighting as mathematical programs for causal inference. Jose has his collaborator, Ambarish Chattopadhyay, on Q&A to answer questions. And after Jose's talk, we have a discussion by Mike Baiocchi. Questions today will be handled by Jingyuan, and I'm switching over to him.
Yes, so for questions, please use the Q&A box instead of the chat box. This will help us to monitor the question and will help Ambarish to answer the questions. From time to time, I'll try to stop Jose to answer questions in the Q&A as I'll read the questions, or maybe I'll reach out to whoever asked the question and let them ask the questions themselves. I guess without further ado, I will just give the mic to Jose.
Thank you so much, Jingyuan. Thank you so much, Georgia, for having me here today, and to all the organizers. Let me share screens. Is it working? Yes, great. So today I'd like to offer a perspective on what I think are three fundamental methods for adjustment in observational studies from the standpoint of mathematical programming. That is, from the standpoint of how each of these methods are acting on the individual level data to approximate or emulate features of this ideal randomized experiment that we would have done in practice. I have to thank many of my co-authors along these years, especially today. I'd like to thank Ambarish Chattopadhyay, Eric Kohn, and Yixin Wang, who wrote the papers that provide the basis for this talk today. And of course, I need to thank my advisor and mentor, Paul Rosenbaum, who has very deeply influenced my understanding of these ideas. This talk is based on these three papers on linear regression, matching, and weighting. And what I'll try to do is to provide a connection between these methods, again, from the standpoint of optimization. To begin, we're going to talk about causal inference. I believe that we should start from the beginning, and that is the ideal of a randomized experiment. So to fix ideas, what is so special about a randomized experiment? I believe I heard Phil Davis say once that no amount of being smart is a substitute for a randomized experiment, and I very much agree. Yet, for many of the interesting policy questions and scientific questions we face regularly, we have to rely on observational studies. And in so doing, I think it's key to follow this piece of advice due to Cochrane, which is that the planner of an observational study should always ask the question, how would the study be conducted if it were possible to do it by controlled experimentation? So what I'll try to do today is to take very seriously this question as we compare these three fundamental methods for covariate adjustment. And again, to fix ideas, there's the experimental ideal, in which randomization is equitable. It produces these two groups that are similar in every way, in terms of observed and unobserved covariates, in terms of the potential outcomes of the units. If in addition we have that these samples of treated and controlled subjects are a random sample from a population, we can say that our trial is representative of a target population. So what are four key features here that I would like to carefully analyze as we discuss these three methods? One is covariate balance. The groups are similar in terms of covariates that we can observe and others that we cannot. Study representativeness of this target population. This notion of self-weighted sampling or unweighted sampling, such that without any differential weighting of the individual unit observations, we have balance, we have representativeness, and the idea is that any differential weighting from these homogeneous weights has a cost in terms of efficiency. And fourth, there's this idea of extrapolation because we have balanced our estimators will essentially be an interpolation of the observed data as opposed to an extrapolation, a property that Jamie Robbins and Ray Rodnitsky and colleagues have called sample boundedness of an estimator. The question is, how are these features present or not in different methods for covariate adjustment? And we're going to focus in the setting of an observational study where the groups tend to differ systematically in their covariates. So the motivating questions, to be more specific, are how are common methods for adjustment in observational studies approximating key features of this ideal hypothetical experiment? We'll talk about matching, regression, and weighting. And the question is, how are they acting on the individual unit-level data that we have at hand sitting in our computers? Unlike other words that have provided very valuable representations of estimates and also the weights implied by these procedures, here we're going to focus on closed form expressions and the math programs that we're actually solving for the data at hand. And we're going to try to compare these methods in terms of 3 dimensions: study design or interpretability, computational tractability or the ability to handle big data today, and statistical efficiency. How good of a use for making of the information provided in the dataset. The setup is as follows. We're going to focus on estimating the population average treatment effect. This is for the most. We can then target more specific estimates, such as the target average treatment effect. And for the most, we're going to rely on the assumption of strong ignorability, which in essence says there are no unmeasured confounders. We can relax this assumption. Again, these methods are a building block for more complex and nuanced methods and identification strategies. So we can extend this also to instrumental variables, differences in differences, and also discontinuity designs. The question that motivates us here is, how are we acting on the individual level data at hand? Okay, so 3 methods for adjustment. I'd like to start by matching, which I think is the one that perhaps more naturally answers to these questions. And here I want to acknowledge that there's a big literature, a big body of work, perhaps starting with Rubin and nearest neighbor matching methods, their formalization by Abadi and Invens, optimal matching by Rosenbaum and Hansen, the work by Gary King and others, and there have been many proposals for matching methods. And there's some nice reviews by Stewart, Invens, also Rosenbaum. And here, what's the idea of matching? I like very much the intuition that Ben Hansen provides, which is that with matching, we're trying to find this experiment that is hidden inside the observational study. So for example, by doing pair matching, we're trying to build these apples to apples comparisons so that in aggregate, covariates are balanced. And hopefully the units are also very close to each other. If there's limited overlap in covariate distributions, that is, if the distribution of covariates in the treated group is different to the control group, we cannot, of course, afford to find good counterparts for every unit in the treated group in the control group. So we match a subset. And then the question is, for whom are we making inferences? Okay. One setting to do matching in this setting, so one approach to matching in this setting is this one that we have provided over the years, where we use tools from what is sometimes called in operations research modern optimization, which in general we're going to use a mixed integer programming approach to directly target different features that we want to optimize in the design of an observational study. So in general, in our observational data set, we're going to solve this optimization problem where we have this objective function composed by these 2 terms, D and I, which on the one hand is trying to find close individual matches between match units, and at the same time trying to match as many observations as possible, so to maximize the information content, if you wish, of the match study. All this subject to matching, balancing, and representativeness constraints. So the matching constraints are going to enforce, for example, a pair matching structure or a full matching structure. and the balancing and representativeness constraints are going to directly balance the covariates, not only one group relative to the other, but also relative to a target population as described by a set of summary statistics. I'm trying to connect this matching approach to other regression approaches and weighting approaches. I want to say a couple of things. One is that if we don't have this information term and we only have the matching constraints, then we recover what is called optimal matching in the sense of optimizing distances between matched units. And on the other extreme, if we focus on this idea of maximizing the information content of the matched sample, we have a problem that we call cardinality matching, because we're maximizing the cardinality or size of the matched study subject to certain design constraints about matching, balancing, and representativeness. And this is going to provide, I think, a closer connection to what happens in regression. So to be more specific, the way this cardinality matching problem may look like is we're maximizing this objective function, which is the number of matched pairs of the study, all this subject to these 0-1 matching constraints. So a unit is selected or not into the study, subject to these two first set of constraints, which in this case here are enforcing a pair matching structure. And this last set of constraints that says that for every category of every covariate P, we have the same counts in the matched treated and control groups, so that we're balancing marginal distributions, and by generating interactions of these covariates, we can balance low dimensional joints and perhaps even the joint, if the data allows us to do that. But what is the point here? The point is that in general, this problem here is an integer programming problem, an NP-hard problem, but it's a problem that in practice, it has a lot of structure, so we can solve very large instances of this problem in typical observational data sets. So, for example, here in a simulation study with Magdalena Bennett and Juan Pablo Bielma, we tested how large of a data set we could match with these methods. And what we found is that we could handle data set with 700,000 of observations and perhaps more in 3 minutes or so, whereas the standard implementation of optimal matching could handle this case, but at least in our explorations, it couldn't handle bigger data sets. So what is the point? The point is that in spite these kind of problems have this NP-hard label, we can solve very large instances of them in practice by relying on modern optimization solvers, and in addition to this, by exploiting some structure of the balancing problem. Here we're exploiting these fine balance constraints, balancing the marginal covariates. And we'd like to extend this so that we're not only finding one treated and control group that is similar to each other, but they're similar to a target population, or that they're balancing the sample towards an individual of specific interest. So here the idea is to extend the previous formulation to balance the covariates towards what we call a target covariate profile. And the idea is as follows, is that we have this target population, which we describe by these summary statistics. Here it's only the proportion of females and so on, you know. And here in the second panel, we have our data set at hand, the data before matching. And we see that in terms of the same profile, we don't have great balance. These summary statistics are quite different. And what we do with this approach is to find the largest sample that it's unweighted, that it's representative, that it's balanced in terms of this target covariate profile. Which is something that I think it's helpful in some settings, because not having differential weights can simplify certain analysis, such as having graphical displays of the outcomes, or using after matching some more complicated methods that do not readily allow for weights. But in practice, this can also be helpful because oftentimes we don't have access to the individual level data of the target population. So, for example, if you're working in healthcare and you're working data with CMS, likely you will not have access to the overall population of Medicare beneficiaries, but CMS may be willing to share with you certain summary statistics of the target population. Well, here by balancing towards this profile, you can still balance these samples, which again, they not need to be 2 treatment groups, they can be 3 or more, by solving one of these different optimization problems for each sample. And the profile can also describe an individual so that we're balancing towards this description of a single patient, for example. In general, this kind of matching problems looks like this, as we described with Eric, is a multidimensional knapsack problem, which is a problem quite studied in the operations research literature, where here we're maximizing the size of the study for each treatment group, subject to these balancing constraints, where we're balancing transformations of the covariates relative to this description. So in the previous example, B was the identity, so we were balancing just each component of the covariates, the mean of each of the covariates. But in this optimization problem, we already start to see how regression starts to appear. Okay, I can talk about rematching after this first balancing step. But first, to connect the methods, I'd like to discuss what is going on in terms of balancing, self-weighting, extrapolation, and so on. Okay, so I said this looks like regression, and to be more specific, now I'll discuss this. Maybe now is a natural moment for questions.
Yes, we do have one question from Q&A. Could you explain the third constraint? I think this is the third constraint in your optimization problem. Is that constraint that makes the optimization complicated? Because standard matching is polynomial time solvable.
Okay, that's a good question. Yes, what makes the matching problem complicated is this constraint here, the balancing constraint. Mm-hmm. Sounds good?
Yes.
And
maybe you want to...
Yes, and the point is that the huge kind of like part of the constraint matrix is defined by these constraints here, and these are only a handful of constraints. So what break the nice properties of the optimization problem, having this kind of like a nice polyhedra that we would ideally just explore the vertices of it, is this part here. So that is interesting because since it's not the entirety of the constraint matrix, there's still a lot of structure here. And what people have found in the field is that, for example, in this fine balance optimization problem, if you have 2 fine balance covariates, 2 fine balance constraints, this problem is still integral. And so it's still polynomially solvable. But if you go from 2 to 3, then this breaks, which is an interesting behavior.
Yes, okay. Jose, maybe you want to go back to the full screen. Oh, yeah, perfect. Yeah.
Okay.
Please carry on.
So regression. There has been great work in this area in economics, sample surveys, statistics, and biostatistics. What we would like to emphasize here are the closed form expressions of how regression is acting on the data. Following here, mainly the work by Imbens and Abadi. Although there's also a history of this work in sample surveys, a nice discussion of this provided in this work by Fuller. So Professor Stigler, one of the historians of statistics, has said that the method of least squares is the automobile of modern statistical analysis. But the question is that when it comes to causal inference, where's the experiment here? So we know that by Cochrane that we want to approximate this experiment, yet when we are just running a regression, in what sense, in what specific ways are we approximating the features of experiments that I mentioned before? So again, how is linear regression acting on the individual level data to produce an average treatment effect estimate, but without resorting to asymptotic approximations? So in this paper with Ambarish, what we do is to provide closed-form finite sample expressions of the implied weights for a range of regression estimators, such as traditional regression adjustments, which is what I'm going to be discussing today. But our analysis also applies to what is often called G-computation, to the stably robust AIPW estimator, regression with multi-value treatments. Our working paper version of the paper also discusses regression after matching, instrumental variables, and by extension, fixed effects. What we do here is to analyze the weights in both finite and large sample regimes, and also to provide diagnostics for linear regression in causal inference. We start by analyzing what may be fair to call the standard approach to regression adjustment in observational studies, where we regress the observed outcome on a set of observed covariates or predictors or regressors, and we're interested in estimating this coefficient tau accompanying the treatment indicator here. And we're going to do this to begin by OLS, although we're going to extend it also to weighted least squares. And the point is that to answer the previous questions about the connection to experiments, we can show that this estimator, this OLS estimator, is equivalent to this uniregression imputation procedure. Uniregression in the sense that we're fitting one regression model in the treatment and control samples pooled, and then based on the estimated model, we predict the potential outcomes under treatment, under control, and we average those predictions. The OLS estimator is equivalent to this procedure. But once we write the estimator in this way, we're in business, because in turn we can write this as a Hayek estimator, as a linear estimator where we're hitting the vector of outcomes by this vector of weights. And the question is how do these weights look like? So in this proposition, we have these closed form expressions for the weights with multivariate regression, where we can see that the weights are basically this uniform term, depending on the sample size, and this other term, which is going to make the weights vary depending, for example, on the initial imbalances between the treatment group and the overall sample. So if we have perfect balance to begin, the weights are going to be uniform, to name an example. And from here, we can go back to our questions of how is regression emulating key features of a randomized experiment, and find that regression is balancing the covariates. That was something unclear to us when we were beginning this project, and it's balancing them very well. It's actually balancing them exactly as opposed to approximately, yet towards a target covariate profile, X star, URI for the uniregression approach, which we can also characterize and see that it's this expression here, which is not the mean of the treated subjects, it's not the mean of the controls, it's not the overall mean, it's some other mean, which I'll discuss more in a second. We can also find that the variance of the weights is given by this expression here, and that this is the minimum variance that the weights can achieve. So intuitively, what regression is doing is to find these weights of minimum variance that perfectly balance the means of the covariates towards this covariate profile X star URI. With one other observation, that the weights can take negative values and hence produce estimators that are not sample bounded. To us, this is interesting because when we analyze the balance and the target population that regression is targeting, and we see the following. So here we're going to return to the famous Lalonde example, where we have this observational part of the study, a treatment and a control group, where subjects were enrolled or not to this labor training program to increase earnings. So here we have a bunch of covariates: age, education, the earnings before the treatment, these indicators for race, and so on. And here we're showing balancing the samples before the regression adjustments with a star and this plus sign. So we can see, for example, that there were these imbalances in age. And here we have the values, the means of the covariates in the full sample before the adjustments with the solid dot. So here the mean is here somewhere in the middle. If this were to be a random sample of a target population, this would be the mean age in the target population. And here with these hollow circles, we're showing what are the means of the covariates in the treatment and the control group after the regression adjustments. And what we find, it's quite interesting to us, and this again is not based on approximations, these are closed form calculations. We can see that the mean of age, for example, is quite close to the treated group, but it's not really on top of it. It's actually kind of like outside its range, which is interesting. And here in this indicator for race black, we can see that the means of these natural populations, as we may call them, the treated group, the control group, and the full sample, are these three values here, but the weighted mean is here somewhere in the middle, which is interesting to us because it's a population that may not exist. So what this is saying is, in a different way, is what Hiro Invens explained in one of his works, is that regression here is taking linearity very, very seriously. So if linearity holds, the intuition is that it doesn't matter where you're fitting your model. If your model is correctly specified, it doesn't matter on which population you're fitting it. But if your model is misspecified, then we can see how fitting this misspecified model around the wrong population can matter. So the implied target population is this one here, as described by these hollow circles. Another regression approach is to fit these linear regression models separately in the treatment and the control group, what we call multi-regression imputation, and then average the predictions. And here we have good balance towards the right target covariate profile, which we can modify, and again with weights of minimum variance, but these weights again can be negative. Okay, so if this is our observational study and we're trying to approximate the structure of a randomized experiment, with uni-regression adjustments, we're achieving very good balance, but towards a population that is hidden in a sense, and with weights that can take negative values. With multi-regression imputation, we're targeting the right population as defined by the previous regression model, and the weights can still take negative values. We analyze this in more generality with Ambarish and provide this theorem that in a way connects different regression approaches and also the IPW estimator. And we find that the adjustments implied by the weighted least squares or by the augmented inverse probability weighting estimator in general can be obtained by the solution to this optimization problem, where we're minimizing this measure of dispersion of the weights subject to these balancing constraints up to a certain extent delta, and making the weights add up to 1. So if delta is equals to 0, okay, then we can recover many of these estimators. But we want delta to vary freely in order to connect this approach to regression to other weighting approaches. Okay. In the paper, we also discussed the large sample properties of the resulting regression estimators, showing that simple regression estimators, such as the simple URI model, is consistent under many underlying conditions for the true unknown outcome and inverse probability models. And we provide this set of regression diagnostics, for example, here, measuring the influence that a specific observation has on the average treatment effect estimate. And all this we provided in a package that we wrote with Noah Greifer. And these considerations, of course, carry over to other settings and designs, such as diff in diff and instrumental variables, where OLS is kind of like the working tool used in fitting the regression models. yet under different identification assumptions. Maybe now is a good moment to ask more questions. Okay, so one question.
Yeah, and maybe you can see it, I guess, Jose.
Yes,
if you want
so
to read it yourself, that's fine.
Yes, one of the questions is how to think about the exact balance property of OLS. I think that ultimately there's a bias variance trade-off between exact balance and approximate balance, and I'm going to discuss this in the next part of the presentation, now in connection to weighting. So, by trying to connect matching and regression, we saw that in the profile matching problem, we were maximizing the size of the study with constant weights that is equivalent to minimizing the variance of the linear estimator with constant weights. And here, in this regression problem, we are minimizing this measure of dispersion of the weights, which for certain choices of the base and the scale weights were effectively minimizing the variance of the estimator. So it's connected in that sense. So now weighting methods. There's a big body of work here. There's a very prominent literature in sample surveys, perhaps following the seminal work by Devil and Sarnall. And then we have work that has been done in econometrics and statistics, focusing on what we call the modeling approach to weighting, more recent works focusing on the balancing approach to weighting, and approaches that connect these two approaches, like the covariate balancing propensity score. And here are some review papers for these weighting methods. So we like to say that there's these two approaches to weighting, which are seemingly unrelated. One is the modeling approach to weighting, where, for example, we fit a logistic regression model for the probability of receiving treatment given the covariates, and then we invert the predicted probabilities to produce the weights. And then there's another approach that in a way says, okay, let's forget about modeling for a second. If what I care about is covariate balance and other features, let me optimize towards that. And one such approach is entropy balancing. A question is, what are we pursuing when we're weighting our observational data sets? We argue that we wait for covariate balance, we wait for stability in the sense of producing estimators that are stable, that they don't rely too much on a few observations, that they have minimum variance, so that our adjustments are interpolation based on the available data, as opposed to an extrapolation that goes beyond the support of the data, and that they can help us to generalize our, to extend our inferences to target populations. A way to think about weighting more formally is as discussed in this paper with Eli Van Michael, Avi Feller, and David Hirschberg, is as follows, where here our estimand is 1/2 of the average treatment effect, the first component, and the same logic applies to the other component, and we want to use this estimator, this linear estimator again, this Hayek estimator, and the question is how to find the weights. Well, one way to find these weights is by looking at the error term between the estimator and the estimand, which one we can decompose in terms of these three terms. This first term here, where here we have the regression of the outcome on the covariates, and this term due to noise, and this term due to sampling variation. The point being that is this first term here the one that controls the bias of our estimator. So by controlling balance, hopefully over a large function class for the unknown outcome model, we can control this bias and do valid inferences. So the intuition, the name of the game, is to balance a large enough function class so that we have valid inferences, and also I would argue protection against getting M wrong, which I think can be achieved by choosing the weights, for example, to be non-negative as opposed to negative. There's room for discussion about this, however. So these two approaches the modeling and balancing approach. The balancing approach is targeting balance against this model class M. The modeling approach is trying to maximize the fit of a model. Well, these two approaches are indeed connected, because if we look at the dual of each of the problems, we recover the other problem. And I'll be more specific about that in a second. But basically, what we document happens in practice is that oftentimes, by focusing on the fit of a parametric propensity score model, for example, we end up having weights that look like this, where a few observations have an undally influence on the behavior of the estimator. But by doing this other balancing approach, which explicitly restrains the variability or dispersion of the weights while targeting balance, we produce estimators that are more stable. One example of this is what we discussed with Ishin in this paper called the minimal weights, which are the minimal weights in the sense that they're the smallest weights in terms of a measure of dispersion, here as defining the objective function, that approximately balance functions of the covariates. We want these basis functions, these B functions, to be expressive enough to span a large function class M, okay? And we want to do it approximately because we want to have the opportunity to trade bias for variance, okay? In some settings, it's just impossible also to exactly balance the covariates, especially if we have too many Bs. So an important choice here is how to choose delta, which is pretty much an open question, although we have a couple of proposals. One example of these minimal weights is what can be called the stable balancing weights, which are the weights of minimum variance that approximately balance the covariates, subject to these weights that are non-negative. An important feature of this approach is that the objective function is quadratic, which is important in order to handle larger data sets. So with off-the-shelf solvers like OSQP, provided by Stellato and colleagues, we can use ADMM to solve very large instances of this problem with more than 1 million observations in seconds. Here for us, the bottleneck became memory rather than computation. And we have a working paper with Kwang Ho Kim and Bijan Nignam in which we explore this implementation as well as other features, such as balancing and RKHS. And what is interesting to us with Ambarish is that if we were not to have these non-negativity constraints of the weights, this weighting approach is equivalent to doing rich regression and imputing the missing potential outcomes based on rich regression. This because we have delta here greater than 0. If delta were to be equals to 0, we would get the usual regression problem. For delta greater than 0, we have this rich regression imputation approach. But something that we don't know how to do with Ambarish is how to recover the behavior of this weighting estimator from regression, because imposing this non-negative constraint on the regression front is something that we don't know at present how to do. So an interpretation of this balancing approach to weighting is like doing rich regression imputation, but in order to produce an estimator that is sample bounded, which to me is attractive because in a sense provides protection against getting wrong the model class M. So the title of this talk was Connecting Matching, Regression, and Weighting as mathematical programs for causal inference. In this slide, we provide a head-to-head comparison of the methods, or instances of these methods to be precise, comparing profile matching to regression to weighting. And we can see that all these methods are minimizing a measure of dispersion of the implied weights or maximizing the information content of the adjusted sample for a given estimator, subject to balancing constraints that we want them to be general enough to span a large model class M. And then what are the forms of the weights that are explicitly used are different. Here with matching, in this form of matching, it's all about study design and interpretability. So we have these constant weights. Here in regression, the weights are free to vary. And here, the weights for example, in SPW problem, the weights have to be non-negative in order for the estimator to be sample bounded. So weighting, as we have discussed it in the balancing approach, is the solution to a convex, more specifically a quadratic programming problem. We implement this in the SPW package for R. With Noah and Ambarish, we have this LMW package to retrieve the implied weights of linear regression. And matching, as I discussed in the first part of the talk, can be implemented with the design match package. Okay, I am running out of time, but here to summarize, we have representations of what the methods are doing in terms of balance, representativeness, self-weighted sampling, and sample boundedness. Here with pair matching, here with regression, the weights can be negative. And depending on the specification is which population we're implicitly targeting, and then weighting with either the modeling or the balancing approach. So a couple of thoughts. Along the lines of the recommendations by Rubin in his work about designing observational studies and so on, and also by Rosenbaum, of course, is that here we're seeing these matching, regression, and weighting methods either as methods that simultaneously adjust for covariates and provide effect estimates, as is often used by regression in practice, by just fitting one model and simultaneously doing these two things, or to separate what can be called the study design of the study, not touching the outcomes, and adjusting first and checking balance and so on, and then doing the outcome analysis. The closed form expressions of the weights allow us to do regression as part of the study design of the study, which arguably is not the case in practice as routinely done. We saw that these methods are quite related, but they're different. I would argue, and people can challenge this, that from the standpoint of study design or interpretability, matching is very, very transparent. It's very clear how it's acting on the data. And I think that the unit level weights, which are constant, integer if you wish, are quite interpretable and can mean a lot to a wide basis of researchers, to a wide audience. And in fact, maybe that's so I think that's also a reason why in high-stake questions, like we want to use methods for adjustment that we know very well what they're doing with the data at hand. And in many of the real-world evaluations of vaccines during the pandemic, these were based on matching methods. I would argue for this and other reasons too, also logistic reasons. From the standpoint of statistical efficiency, we see that the implied weights of matching are costly. They're very constrained. The ones of regression are essentially unconstrained. So in terms of efficiency, I would argue that these methods are preferable. And then in terms of computational tractability, in general, the matching methods that I presented are these NP-hard problems. So the other methods would more readily scale to larger data sets. But the point is that here, we should not shy away, I think, from these more difficult matching problems because they have the NP-hard label, because in very large instances of these problems, we have been able to solve them just fine, which is, I think, is an interesting behavior of these general IPs and mixed integer programs, because in the typical instance, there seems to be a lot of structure that can be exploited by generic solvers. I wish to thank Picori and Sloan for their support, and stop here at the 45-minute mark so that Mike can provide comments. Thank you a lot.
Thank you, Jose, and thank you for staying on time. We do have a question in Q&A, but let's move to discussion first, and then if we have time in the end, we can get to the question. So Mike, if you want to share your screen and lead us to the discussion.
Sure. I think I need to switch it. Is this now showing the full screen?
Yes.
Yeah, great. Jose, I'm very impressed about it. Like, you were exactly 45 minutes. That was commendable. So providing commentary, like, it's a little bit of a challenge. What do you do? I mean, this person just explained their research in really great detail. And so do I just retread that? Do I summarize? I'm going to go for trying to place this work in context, and very large context, and sort of like what is going on in causal inference, what is going on in data science level kind of thing. So I am trying to provide like sort of friendly commentary to like other sort of junior causal inference folks, maybe like sort of screw tape letters kind of thing here. So let's start where Jose did. What was he doing right at the very beginning? Well, it starts with thinking about sampling and randomized control trials, which is where a lot of us who are trying to describe causal inference start, because that's where we reach back and we look at that because it is a very strong form of inference for us. And why is that true? Well, that's because as statisticians, we create a data generating function. We reach it in the world, we cause something to happen, and then the following forms of inference are predicated on that. So it's almost like a geometry or something like that, where it's like, yes, it's rigorous mathematics, but it is something where we can find an intersection with the world. It's not propositional, maybe the way like models are. We don't conjecture that something is linear, and then we try to like argue that that might be true. The reason we keep reaching back to these forms of inference and causal inference because they are the strongest ones we know. If we could find something in the real world that looks like that, maybe it's slightly divergent, maybe we have to do a sensitivity analysis, but we're getting close to that. So that's usually, if you ask most of us, we'll probably give you some argument like that. What Jose's doing is slightly different. He does that, but there's also a really important part here, which is that sampling and RCTs are transparently convincing. So when we think about them, we've spent a lot of time thinking as like causal inference folks, but to our collaborators, they can almost see what's happening. They can think about, if I broke these two into groups and I did it in a random kind of process, but maybe I like did some blocking. Now I can think about, if I set them into the future and like watch what happens, like, yeah, that will probably convince me that there's some causal difference there. So don't get confused. There is both of these happening, but I'm going to emphasize the part which I found very interesting and very instructive to me, which was Jose pulling out these features, and that other people have thought about as well, about different features of, let's just sort of think of this as like randomized experiments, but some of this applies to sampling as well, about why we should be convinced or why we find these useful forms of data generating functions. So covariate balance, study representativeness, self-weighting sampling, and sample boundedness, which are not, we spend a lot of time, I think in general in causal inference, thinking about covariate balance, and maybe like we think about transportability and that kind of stuff, but some of these other ones are a little bit subtle. So I'm gonna like emphasize a little bit more some of the self-weighted sampling and sample boundedness. At the core of good causal inference is convincing. All right, like, sometimes we forget, especially the academic statisticians in the audience, that like we think it's all about like proving fancy theorems and that kind of stuff. But we are really being held to task that like we need to take real world data, compress it in a useful way, and then give rigorous conclusions to our audience. Like that's our job. Like that's, I mean, yes, we're some of us are trying to get tenure, so we're gonna do some fancy math, and like Jose does that, I'll point that out. But we need to be able to draw these rigorous conclusions. And if you haven't, and again, if you're like sort of a younger statistician, even you're sort of like the Middle Ages statistician, check out Bradford Hill. So the environment and diseases in the 1965 paper, and if you've seen this before, there's like the Bradford Hill criterion. Everybody sort of like loves like trashing and that kind of stuff because he didn't get it right. But if you read that paper, you can see that what he actually sort of he takes a stake where he says, t-test is super cool, but like, who cares? I'm here to reach into the world and say like, hey, that might be dangerous. We need to shut this machine down. He's making those kinds of calls, which are causal conjectures in the under uncertainty, and it just really, when I read this, it really like hit me that our job is to, as causal inference people, sometimes. And I really like Jose's lecture because there's two parts. And so for his first part, there are sometimes when we are interacting with an audience, think like a medical doctor, or we're thinking about like a policy, educational policy person. We need to create an analysis that we can hand over to them that they can look at, and they could say, hey, I don't like this. I find this is wrong. Here's where I think you've got the analysis wrong. We need to be able to hand over data-based arguments that will either be convincing or not, but they can be interrogated by the people we're talking with, right? And so at least two discernibly different audiences, Jose engages at least two different audiences during this. So let's start with profile matching, which I think is a very clever, very thoughtful way to think about building out some of this. So again, lots of different things going on with profile matching, and I'm simplifying down, but when he was engaging this, he's talking to an applied audience. He's thinking about, I have a profile. Listen, I'm going to go talk to my applied colleague and say, where are you going to think about this causality coming into the world? Describe that to me. Give me a profile. Maybe it's like, these are the kinds of students, or maybe it's Tom. We want to think about happening to Tom. And that's also sort of a neat feature of profile matching, that we can maybe zoom in and think about heterogeneous treatment effects down to individuals. So, but you describe a profile, dear colleague, and I will generate a study design that will get you in that native language that you just gave it to me, some analysis that will be fairly rigorous, and you can interrogate that. And the emphasis there, I keep using this kind of hand gesture, partly because I'm probably descended from Italians, but like the other thing is that like we're pinching, or we're going down to individual weights, right? We're not expanding, we're not contracting. We're talking to an applied person in their native language that they can use their intuition, right? So when Jose is invoking the idea of self-weights, he's constraining our analysis and our flexibility, our mathematical structures to only be built out of Lego pieces that look like Lego pieces that our applied collaborators can think about very easily. They've built a lot of experience that we don't have, right? We get data sets. They have lived experiences. So when we keep our analyses in these self-weighted units, they can bring to bear knowledge that we don't have. We are really great with data, but they have deep experience that we don't have, right? So, and again, I love this. Go through this paper. There's a lot of like nice little gems along the way. But I don't want to like undersell this. Like, the hard part here really is like knapsack problem, right? Like cool, like optimization. How do we implement this? How do we do that? That's our job, statisticians. We're and sort of data scientists in general, but we're doing it off stage, right? The hard part is not for our applied colleagues. We bring back an analysis that is in their language, and we do all the hard part off stage. We get everything prepped. That's where the hard math happens. It shouldn't happen in front of them for this kind of target audience. So again, let me get that clear. It's like he's talking to an applied audience at this moment. He's thinking about people who are going to describe in their own language a profile for where the inference is going to happen, or where the causality is going to happen. And then it's our job to do hard math and bring things back that will be very convincing. Then in the second half, or second part, Jose starts thinking about linear regression. And we've switched to a different audience. We're dealing with a little bit more of a sophisticated audience. Maybe, I mean, I don't want to say that much more because they're like just economists, right? Because they're not that sophisticated. I didn't look through the attendance audience. I'm sorry how many economists I just made that. But linear regression, it's out there. The computation is super fast. The linearity makes sense, and it's everywhere, right? So it's a really important part of causal inference, even if like maybe we've all been taught about all its problems and we think about that. I'll tell you, like if you asked me, or if you asked like any of us before we started hearing Jose talk, we would know that there's like, yeah, under certain circumstances, we could get kind of close to causality, but I couldn't have thought through quickly what the implied weights are, or something like that. Or sorry, I should say the implied study design. I could probably tell you something like, hey, it's maybe like conditional on the covariates you have, and there's something like, but I wouldn't have thought like carefully about those weights. And that's really, important. And circling back to, I'll say, sorry, I'll return to that third bullet point there, and just like another slide or two. But like, what was the like sort of the payoff of this line of research, or this like sort of paper, is like, there's a moment where where Jose points out like, yes, it achieves the exact balance under some conditions, but maybe, and that's like useful. That's one of the 4 criteria that we sort of think about in sort of experimental designs that like are super useful for if the 2 groups looked alike at baseline, and then we walk through a few, but because he was very careful, and his collaborators, I should make sure to say, his collaborators are very careful about this, there are other ways in which it fails. And the payoff really is, and this is why you have to read this paper. This is really useful. They've now got some nice plots, some ways of thinking about and interrogating for this type of audience, for economists, for folks who think about causal inference using linear models, ways to assess if some of the other criteria or like features that we find convincing about experimental designs are failing. Right? It gets one thing, exact balance, but like, hey, we've got like negative people or something like that, or like, like there's some weird things along the way that you might want to assess because it may cause problems. And now we can look at that more carefully. That's the kind of payout that we're getting. All right. So the last two major points that I'll make, this slide and the next one. Groping inside of causal inference, I'll tell you, like, so I sort of got my PhD in 2010. There's a lot of different tribes running around inside of causal inference, like the matchers and the inverse probability weights and target maximum. Like, there's like just lots of folks running around. And sometimes they talk to each other in openly positive ways. And we all knew that they were sort of different. And maybe you would say something like, hey, matching thinks about like one-off random, causal sort of exposures, and maybe like inverse probability weight are sort of more epidemiologists. So they're thinking like longitudinally or something like that, lots of different exposures. Maybe target maximum likelihood grew out of like a different culture where there's like better measurements of folks and the behaviors are a little bit like differently constrained, something like that. You could. But what Jose is trying to do here and his collaborators, they've been thinking very carefully, not about directly contrasting them, but sort of like a Rosetta Stone. They're moving things into experimental design framework, thinking in terms of the weights. So we now have an ability to sort of, and other folks have done this as well. I don't want to say that they don't, but like they've done a really nice job of making it easy to move into something that we feel comfortable with, experimental design, and then move back out to another method. And it allows us to think very clearly and carefully about where the wins are, the differences, and that kind of stuff. Again, I think a lot of us carry these intuitions, but now it's like written out in very nice detail, and it's a wonderful addition to the literature. Here's the last piece I want to leave you folks with, and this is really, I'm getting meta, is right now, sitting in this time period, there's a lot of different data science cultures. If you're on this call, you are probably self-described as something like a causal inference person. We are all competing for different attention. And this is sort of like, I'm calling out the machine learning folks in the sort of black box in particular. If you've been on Twitter, if you've been anywhere, like you've seen like Chat GPT and it's like, holy cow, this is like magic. Like there's another data science culture that has come along, is doing massively interesting things. We wouldn't have done that, right? Like there's no person who's like going to build up language models in a causal inference way and get to there. What are they doing? They're doing something different, right? And we started to engage them. We started thinking about like pulling black boxes apart and maybe using some causal inference or sampling things to get in there. There's some really neat work on that. But I want to like pull you back and put this in contrast with the stuff that Jose and his team is doing right here, just to sort of reassure you that what we are doing is very interesting and very different and is differentiated, right? When they build their algorithms, their proof is in the sort of like prediction space. We have built up rigorous arguments where we are trying to convince people that the pieces along the way work, and that the conclusions themselves should be doing the things that we think they're. Also, in particular, let me try to say it this way too, is Jose's team is also trying to keep our analyses in the native language or in an accessible way, a way that can be challenged when we hand the analysis over. When you use like a sample weight, or you think about the boundedness and you think about like, hey, the regression is putting the weights in the wrong place. There's like nobody there, right? Like when we were with a hypothetical population, may not even exist. Are we even doing something? Nobody cares about that in machine learning. Like that's not the GPT-3, GPT stuff, like nobody's talking, nobody cares about that, but we do, because we're going to hand this over and people are going to interrogate and pull apart our analyses. And that's the right thing. If we're going to make, like Jose ended it this way, it's like, we're going to tell people what to do with COVID and people are going to die. Like we need to be very careful. And on our job, we also need to give an analysis that can be assessed by other people who have different skill sets. I'll leave this with this is a proposition, is I think our unique strength as statisticians, as causal inference people, is we are very thoughtful in a way that other data science communities are about what data should come into existence, right? So again, going all the way back, sampling frameworks, randomized experiments. The reason we retreat to that when we're under pressure is those are the strongest forms of inference that we know, and they are about as strong as we can ever get. And we are thinking about given a study or given a question from our applied researchers, what do we do? What data should be there? What can we do to bring in like the best quality data to answer that question? That is our strength. We are different than other fields of data science because we think about what data should come into existence. Even when we're being observational, right? The big win since like the 1990s is the design features of causal inference. And it's a lot of what like Jose and his team was talking about today. It's like, you get a data set, let's whittle it down, or let's move, like let's upweight and downweight such that the data we are about to analyze is the stuff that would answer the question the best. So don't get, be impressed. Machine learners are doing fantastic things, but the causal inference community has always been doing something very important, which is creating rigorous designs that think very carefully about what data would really answer the question, right? And you see that through and through the work that Jose and his team has been doing today. So I want to say congratulations on some very excellent research, and you all should go and read their papers immediately.
Thank you, Mike. I thought that was a great combination of a talk and discussion. Thank you both. Jose, do you want to respond to some of Mike's many comments?
I have to say that I learned a ton from listening to you, Mike, and emphasizing and explaining so articulately how what we do connect to what scientists and policy analysts are doing, and ultimately what they care about. So I think that you articulated that way better than I did. Thank you. Also for your generous the description of the work. I wish to answer one of the questions here in the chat. It says, any suggestions on which approach might be preferred when ignorability is violated, as it almost always is? I agree. Strong ignorability is almost always violated. However, the point is that these methods are the building blocks to be used under different designs, different assumptions. For example, with instrumental variables, you can use matching or weighting or regression. I think that what we try to do today in the presentation is to differentiate this method in terms of, again, study design and interpretability, efficient use of the data at hand, and the ability to handle large problems computationally. And in my mind, there isn't a winner along the 3 dimensions. So it depends, again, on who's your audience, as Mike is saying. What would you like to emphasize?
All right, thank you, Jose. Let's wrap up the seminar then for today. And in fact, we are wrapping up the seminar for this year. So we will see you again in January. We are doing something special in January. The 4 talks starting on January 10th will be a mini seminar series on causality and fairness. So we hope that we will see you all on January 10th. Thank you for your attention and Happy New Year.